So let's get back to Visual Studio 2013. Expand the Lesson 3.1 project and make it your startup project. If you look at the program.cpp real quick, you'll notice that it's the same software as before, and the renderingame.h file looks strikingly similar to the Lesson 1.3. The only difference now is that we're using a color triangle demo instead of the point demo. And likewise for the implementation, we're initializing that color triangle demo and deleting it during shutdown. Otherwise, it's the same code. It's the color triangle demo then that we're going to focus on. So open up the color triangle demo.h and CPP files. But really the first thing that I want to talk about is the color triangle demo.vert and fragment shaders, the vertex and fragment shaders. So in the previous application, we hard-coded our point demo fragment shader and vertex shader. Specifically the fragment shader, we hard-coded it to a position in the screen, but that's infrequent. That's a rarity. What we really do is we accept those locations from our application. And the way that we do that is through, I said through a vertex buffer, but we're also talking about vertex attributes. So inside of the vertex buffer, we're going to identify particular parts of the vertex buffer or of our OpenGL buffers, period. I'm going to call it the vertex buffer because we're storing vertices in this particular buffer. And we need to identify inside of that buffer what data is what. And we're going to use vertex attributes to do that. That's what you're looking at on the screen right here. This vec4, it's named position, and another vec4 is color. So that means that each vertex that's coming into this vertex shader is actually made up of 8 floating point values. 4 floating point values for position, 4 floating point values for color, and that we mark them both with the in modifier that makes them input variables. And these are layout location modifiers, and I'm going to talk about that here in just a second. Notice now that we still specify our GL position, and this time instead of hard coding it to a value, which we did before, we hard coded it to a vec4 of 0001. Now we're not hard coding it, but instead we're passing that input position vector to the GL position output. Now also, just to spice this up a little bit, instead of hard coding the output in the fragment shader, we're actually going to assign the color of the vertex shader and pass that through from the vertex shader to the next stage in the pipeline that will actually use this data, which is the rasterization stage. And so the position and the color are going to be passed out of the vertex shader into the rasterizer stage. Rasterization happens for our triangle in this case, and then that data, the rasterized data, is being passed to the fragment shader. So notice how we're doing this as well. We're using a structure also labeled with the out keyword. So this out keyword modifier says that this whole structure is an output. And notice that this looks like a C-style struct. It has data just like a C-style struct, and it has a name. We've named this particular instance of this structure. Not only are we declaring the structure, we're also creating an instance of it with this syntax. And I'm accessing the color member of that structure with the dot operator, just like you would in C. I've named this vs_output. That's just a convention that refers to the vertex shader output. And of course, I could have dropped out the construct of a C-style struct altogether and simply had out vec4 color. The reason that I'm not doing this is just to make this more readily extensible. Now let's look at the fragment shader. The fragment shader has an input structure that is the very same name and has the very same members as the output structure of the vertex shader. Now its output then, so I've named that in, and it's marked in and it has a name in. And now I still have the same output color vec4. But notice now that instead of hard coding that color to red, that color is in.color. So what was passed into this shader stage is going to be coming out of the shader stage. And you'll see what that does here in just a moment. So let's go take a look at the triangle demo header.h file. It's a drawable game component. It overrides the initialize and draw methods. It has a shader program and a vertex array object, just like we did before. Now we have a vertex buffer. This is something new. The vertex buffer is the whole point behind this lecture set, so let's talk about this in depth. Lastly, note this thing. These are those layout attributes. I've described these as constants inside of an enumeration called vertex attribute, and that just gives me the value 0 and the value 1 so that I can refer to their layout indices by name rather than by a magic number in my code. So those two values, vertex attribute position and vertex attribute color, they refer to location equals 0 and location equals 1 because I've specified their values as 0 and 1 here in the enumeration. You'll see how those are used in just a minute. I'll take a look at the implementation of the color triangle demo class. As before, we need to compile and link our shader programs. But I'm going to refactor this a bit, because if we go back to our lesson 1.3 and we look at our point demo code, we can see that there's some reused code here. There's quite a bit of duplication that's going on there. Well, instead of duplicating that code over and over again and possibly introducing bugs, let's refactor that into a method called build program. And let's create a class called shader program that can store it. So this is kind of an interesting idea where what we'll do is we'll build up a set of shader definitions. And all the shader definition is an enumeration and a string. So the enumeration to specify what type of shader it is, in this case GL vertex shader and GL fragment shader, and then the string to specify its location. That vector of shader definitions is what we'll pass to our build program method. So let's go take a look at our build program method inside of the shader program class. This is a new class that you're being introduced to. And this class, let's look at the header file of it real quick just so you can see it. So this shader program has an mprogram GL unsigned int. And that unsigned int is just like the unsigned int that we've used before, but this time we're actually using a shader program wrapper. That's all this is really, is a thin wrapper to this idea of a unsigned integer referring to a shader program. So the implementation of the shader program for build program starts here. We have our input vector of shader definitions. All we're going to do here is iterate through those shader definitions and call compile shader from file. Now, compile shader from file, you're going to notice right off the bat is going to be very, very recognizable. You call that utility load binary in order to load the shader source, find its length, call the GL create shader code just like you did before, and then GL shader source, and finally GL shader compile. There's one additional step that we're doing that we didn't do before. Shader compilation can fail, right? It can fail for a variety of reasons. If you've been following along and hand transcribing any of this code, you may have run into a syntax error or two. So if that happens, we want to know what happened. And to do that, we can check the compile status by calling get GL shader IV and passing the shader name that we've just compiled and the GL compile status enumeration. And then the output of that is a compile status on GL int. Now that GL int, if it's not GL true, then something went wrong. We don't know right off the bat what went wrong. We have to query the log. We have to go get the log to find out what happened. And we can do that with get shader IV, passing in GL info log length in order to get the length of the log, get a string, reserve the length of that string so that we can call GL shader info log, and we can get back that data for the log. We're going to use that just as a plain old string in a game exception that we throw. So this is just a bit more verbose version of the code that you previously did. So we're compiling each of these shaders. That's what we're doing inside of this for loop. Called GL attach shader for each one of the compiled shaders. And then we call GL link program for our M program. The link status here can fail just like the compilation status can. And it follows the same constructs, right? In order to get the link status, we call, instead of get shader IV, it's GL get program IV. And that's an integer vector is what that IV stands for. So get GL program IV passing in GL link status in order to get an int back. And if that int's not GL true, then we can go query the log length again. And from that log length, we can allocate a log, go get the log itself and report an error back. Now, when we're done, this last little bit here is to simply delete all of the shaders that we did that we had compiled temporarily. This is identical if we go back to our 1.3 point demo class again, and we look at what we did at the bottom here. That's the same steps. All I've done then is refactor this code just to make it into a method that we can recall over and over again. Okay, so let's go back to colored triangle demo. We've now built our program, and this mshader program is a member that's now stored inside of our color triangle demo class. The next thing we're going to do is create a vertex buffer. Now, to create a vertex buffer, the first thing we need to do is create a set of names. Go get a set of names for the vertex buffer. And a vertex buffer is just the GL unsigned int, and GL gen buffers generates one or more vertex buffers, and we're going to specify the number that we want. We just want one vertex buffer in this example. And then GL bind buffer associates that name with a particular target, in this case, GL array buffer, and that GL array buffer specifies that this is the data stream that will be used for vertices. And then finally, GL buffer data specifies the data that we're going to put into. This is how we populate that buffer. And we're going to populate that buffer, that GL array buffer, from this static vertex position color array. So I've got a vertex position color data type. it just looks like this. It has a GLM vec4 for position and color. This is going to start to add up here real quick, right? We're going to see our vertex position color means we've got a position and a color for each one of our vertices. And now our set of 3 vertices, 3 for a triangle, we've got one whose x value is 0.75 along the positive x-axis, negative 0.25 along the y-axis, so this is down here a bit. This is in screen space, this is in homogeneous clip space. And then 0 on the z-axis. In fact, all of these are 0 on the z-axis. 1 because these are all position vectors, but in fact, we're not going to use these 2 components at all. And its color is red. So the next one is 0 on the x, but 0.5 on the y. So if you can imagine in your head what's about to happen here. We've got a point that's going to be to the right and down below the center of the screen. We've got another one that's going to be half the distance to the top of the screen and aligned with the y-axis. And another one that's to the left of the screen and down a bit. And those are red, green, and blue vertices respectively. We're passing those into the vertex buffer with GL buffer data. And we're using this flag called GL static draw, where GL static draw says to OpenGL that the vertex shader will be used to draw many, many times, but it won't be modified. So the next thing that we'll do is create a vertex array object. And remember I said I would come back to this concept, that we needed one, but I really didn't define what it was. Well, a VAO, a vertex array object, allows us to store the state of these calls. Where are the vertex attributes for our vertex buffer? It's a cache of sorts. Right? It's saving state. And what happens when we call GL bind vertex array is we are now restoring those states so that we don't have to make these calls over and over and over again inside of our draw call. We certainly could do that, but there's no reason to because we can cache them inside of a vertex array object. So we're going to bind our generator vertex array objects. We just want one. And then we're going to call bind vertex array objects so that it's now active in the OpenGL context. These paired calls are GL vertex attrib pointer and GL enable vertex attrib array. Remember in our vertex shader, I called these vertex attributes. Now, in our buffer certainly has this notion of a position and a color, separate attributes. But what our vertex buffer really looks like to OpenGL is just a stream of bytes. It has no idea how those bytes should be interpreted. We need to tell OpenGL how to interpret those bytes. And that's what GL vertex attrib pointer does. This call, the very first argument to this call, is just a number. And I'm using the enumeration vertex attribute position, which comes from that enumeration. Vertex attribute position 0, vertex attribute color 1. I like to do that because I don't like magic numbers in my code if I can help it. Now that said, I'm creating a magic number, which is the number 4. But that number here means I want 4 GL floats to be associated with the location 0 in the vertex buffer. The location 0 for our vertex attribute has 4 floating point values. The next argument is GL false. This defines normalization. Should this value be normalized? This will always be false if a GL float was specified. If it was specified as an integer value, then this could be true, and if it was true, then the values would be normalized by dividing it by 255. So an 8-bit value can range from 0 to 255 unsigned. So that in floating point, if I wanted to normalize that so that its values were between 0 and 1, I would divide it by 255. Well, that's what GL true does for us if we specify that as GL true when the value is integer. The next value is the size of one vertex. So that's the idea here, is how big is one vertex. So that's the size of vertex position color. That's the type of data that we're storing in there. And then this last value is where in each stride should we find the position color. And there's an offset of macro that says pass in the data type, pass in the name of the member of that data type. So if we go back to our vertex position color, this is position and color. Those are the members that I'm talking about. When we specify that member to offset of, it says, well, this is n bytes. In this case, it's 0 bytes. It's the 0th element, it's the first element. I still use offset of even when it's 0. I could have just hard-coded it to 0, would have done the exact same thing. I don't like to do that. In case for whatever reason, I come in and I swap these two things around. If I put color up here and position down here, my code will still work because I called that macro. The next line is exactly the same because I'm specifying another vec4, but this time for color. So the offset of macro for color is what's used there. I called GL binder a vertex array 0, and I do it at the end of each draw call, and I want to explain why I'm doing that now. GL bind vertex array 0 unbinds the vertex array object that I had bound previously. Now, the reason that we do this is really for safety. Remember that this demo And I realized that in each of the lessons that we were doing here, I'm trying to isolate the code as much as I can just to make it a simpler demonstration. But really, this lives in a sea of other code. So it's very, very possible that other code could be modifying vertex buffers as well, other GL vertex attribute pointer calls. And if we left this vertex array object bound to the context, it's very possible that something outside of this class might modify it, and we don't want that. So those kind of side effects we want to avoid, and that's why we do GL bind vertex array 0. Lastly, before we actually look at the output, we call draw. We bind our vertex array object. Remember, that restores the input layout, so to speak, the layout of all of our vertex attributes. We call GL bind buffer, and this time we specify GL array buffer and our incoming vertex buffer, just as we did before here. GL bind buffer, just long and short of it is, you need to bind those buffers to basically tell the pipeline, this is where my vertex data is. Remember, I could use the same layout. The good reason for not doing that in the VAO is that each of these vertex array attributes, the input layout, can apply to multiple vertex buffers. So I could have lots of vertex buffers that all have the same layout, and I can specify them differently using GL bind buffer. Now, again, I want to specify GL use program to specify the shader program that we're going to use. And this time, I'm just using an accessor for mShader program. That shader program class just returns the GL unsigned int mProgram, just as we did before, just inside of an accessor this time. Now, lastly, instead of GL draw arrays or draw call drawing points, this time we're going to call GL triangles as the enumeration. We're going to specify 0 as the offset, and I want 3 triangles. And when we run this application, here we go. Here is our triangle. So this is all in screen space. Usually our triangles need to be transformed. We'll talk about that here in just a bit. But remember back from our array of vertices, we had 0.75, so 3/4 of the way to the right hand of the screen and 1/4 of the way below the middle of the screen. So this is about the middle of the screen here. And its color is red, and then green, and then the blue vertex. And remember that discussion that we had about the pipeline where we talked about the rasterization stage, where the rasterization stage says, okay, for each of the colors that are coming in, well, each individual pixel that is going to be drawn is going to be interpolated between those 3 colors. So notice how the further away that I get from red or the further away I get from green or blue, the less color is dominated by that vertex color. And that's interpolation in a visual form. So that's a look at OpenGL buffers. In the next demo, we're going to talk about passing uniform data to shaders.